In this lecture, we will look at rotations about one of the coordinate bases, which is the simplest of the rotations. To start with, let's look at two-dimensional rotation, where we want to rotate this point to this new location x dash, y dash. The original location is given by r cos phi and r sin phi, where phi is the angle from the x-axis. Now, after rotation, this angle increases to phi plus theta, and hence we have phi plus theta cos r to give us the x dash, the new location of the point, and y dash as r sin phi plus theta. Now, if you use the formula for expanding cos phi plus theta and sin phi plus theta, we will get this representation. How exactly, we will look at the formulas in the next slides, but let's look at this representation closely. This seems to be the representation of x dash and y dash as x and y with some weights, alpha or beta. So this cos theta and minus sin theta and sin theta and cos theta can nicely fit into a rotation matrix. Rotations in two dimensions is equivalent to rotation about the z-axis in three dimensions. And if you recall from the previous slide, we got x as a linear combination, we got x dash as a linear combination of x and y with these weights, and they are present here in this rotation matrix. And we got y dash as a linear combination of x and y with these weights. So they form the top left corner of the rotation matrix. And because this is a rotation about the z-axis, the z coordinates is not going to change at all, and hence z will get multiplied by 0, 0, 1 and will give you exactly the same value as the previous value of z, which makes sense because if you're rotating a point about the z-axis, the z-axis value does not change. Now this rotation matrix, if we multiply it with point P, we will get P dash as our new location of the point after this rotation has been applied. Now let's look at the rotation about the z-axis a little bit more closely. So this is the original location of the point with x, y, z coordinates equal to r cos phi, r sin phi, and because our object is on the xy plane, z is equal to 0. The z component is 0. Now we want to derive our new location x dash, y dash, and z dash. So we still calculate z dash even though we are performing rotation about the z-axis, as we know that the z-axis is going to turn equal to the previous z location, which is 0, but still. So this is our rotation matrix, and this is the basically the current location of the point, and we want to find out the new location of the point after this rotation matrix has been applied. If we consider the rotation matrix that we derived in the previous slide, with the weights of x dash inserted here and y dash inserted here, right? And there are 0 weights for the z coordinate basis with 1 over here, so that the z coordinate doesn't change again because we are performing rotation about the z-axis. Now this is again the same original location of x, and we are multiplying this rotation matrix with the current location of x, and after this matrix multiplication we get this, which is a vector. So we have a single term here, we have a single term here, which is the y coordinate, and then the z coordinate, and because this is a point, we have a 1 here in homogeneous coordinate system. Multiplying this rotation matrix with a point still gives us a point, so still gives us a 4 by 1 point, where the fourth dimension is just simply 1 to specify that this is a point. Now looking at the trigonometric expansion, we use this formula for that. So cos of theta plus phi is equal to cos theta cos phi minus sin theta sin phi, and sin theta plus phi is equal to sin theta cos phi plus cos theta sin theta. So if these are formulas, and if you're ever required to do these calculations, you'll be given these formulas. Now multiplying the current location with the rotation matrix gives us this is from the previous slide. We substituted the values of these with this, and r was taken common, so we got r cos theta plus phi, r sin theta plus phi, and hence we get to our original form where we said that x dash is equal to r cos theta plus phi and y dash is equal to r sin theta plus phi, and hence we have proved that our rotation matrix that we derived was correct. And of course z dash is equal to 0 because our z coordinate of the original point was 0. But we can write this in general form, that the new location of x dash would be equal to x cos theta minus y sin theta, and the new location of y dash will be equal to x sin theta plus y cos theta, where theta is the angle of rotation. So theta is our angle of rotation, and the new location of z dash will be equal to the previous location of z dash because we are performing rotation about the z-axis. Now using similar methods, we can derive rotation about the x-axis and rotation about the y-axis. So we can use similar arguments, and for rotation about x-axis, x will be unchanged because we are performing rotation about the x-axis, and if you are performing rotation about the y-axis, y coordinate will be unchanged. This is the rotation matrix for rotation about the x-axis, and see how we have a unity over here, which is the x-axis will not change, right? And we have similar cos theta minus sin theta cos theta values here. Over here the sign changes, we have a positive sin theta over here and a negative sin theta over here, and we have these columns and rows as 0 1 0, which specifies that the second coordinate, which is the y-axis, will remain the same, will get multiplied with 1, and when we are calculating the y-axis, the value of the new y-axis location of the point, it will be the same as the previous y location.